rather than try to replicate the most difficult or more difficult types of copper artifacts, we set out to replicate what we thought might be the simplest. It certainly appears to be the most common. And our goal then was to establish some sort of baseline of how long it would take to make such an artifact.
About 1,000 years ago, native people living in the western subarctic, what is today Alaska and the Yukon, began using copper. For thousands of years, inhabitants of this area fashioned tools out of stone, wood, and animal tissue. These several hundred-year-old arrow points, made out of caribou bone, are an example of a tool from this time period. In this copper-rich region, native people began using copper probably as early as 1,000 years ago, and they were still using copper when Euro-Americans began to enter the region in the latter half of the 18th century. In the early 20th century, more copper ore was mined here than anywhere else on the planet, but the copper used by the indigenous people is known by geologists as native copper, meaning it occurs naturally. This copper was not mined from bedrock. Instead, native people collected nuggets such as this one shown in the gravel bank of Kletson Creek. Miners and geologists have noted the presence of native copper nuggets in more than 50 streams and rivers in the region. The names of some streams are derived from the northern Athabascan word for copper, such as Kletson Creek and Chittistone, shown here. Several different native groups used native copper, but northern Athabascans were the biggest users, especially the Atna. Native copper has been found at almost 80 archaeological sites in Alaska and the Yukon. Most sites have only one or a few artifacts, but 170 were found at the Golcana site and 138 at Donkadinine's village. At both sites, the Atna worked native copper into familiar tools, like knives and arrowheads. Over 60 of the copper artifacts from the Golcana site don't correspond to any specific tool. These may be bits and pieces left over from making tools out of copper nuggets. By far the most common tool in the region are the awl and awl-like shapes. An awl is a tool made out of bone, stone, or metal used to make holes in leather or wood. Indigenous oral history provides some clues as to how native copper was worked, but in order to better understand the process of turning nuggets of native copper into tools, and perhaps to better understand the copper working debris at the Golcana site, Purdue University Anthropology Professor Dr. Kory Cooper devised an experimental archaeology project.
What's being filmed today and previously is experimental copper working, which is part of a larger research project. And so the work that is being done by Mara and Jenna is going to provide us some very basic but currently lacking and very important information about really the origin of metallurgy.
Nice.
Which was hard to do because, you know,
Yeah.
you gotta hold it, but
Yeah, being that they're so small.
And so these were just pounded out from a nugget, but you have some that were made from like taking the nugget and pounding it flat and then folding it too, right? Some of those are...
Yep.
It's the hammering of native copper with rocks and annealing native copper. This is generally regarded as the first metallurgy that was performed in the ancient world. And we have evidence from archaeology that native copper was being used in North America, the region around the Great Lakes, by about 7,000 years ago, or perhaps even a little earlier.
We are using native copper nuggets provided by Professor Cooper that were found in Alaska, and we've chosen a couple of nuggets that are similar in weight to the awls that we were trying to replicate. As you can see, they have a bluish green color, and this is due to the oxidation on the surface, which is a chemical reaction that happens when the copper is exposed to the oxygen in the air. This would have made it more distinguishable from other rocks to the Atna people. We're going to start by using the cold working technique, or cold hammering without heat, to see how easily we can shape the nugget. The hammering will be done using lithic or rock tools found in the creek behind us. We've found that a large coarse grain rock works best as an anvil to give support during hammering. So we found that a coarser grain rock works better for hammering, also something with more of a flat surface, like this. We believe the Otna people would have used something similar to this. The first step to cold working is to lay the copper nugget on the anvil and hammer down in a controlled direction. So first we would like to get all the oxidation off. As you can see, it kind of just comes off on the rock there. It helps to hammer, turn, to kind of get a general shape. This type of hammering is also called forging. After you've been hammering for a while, you can start to feel the heat coming from the copper. You want to keep hammering and then turning to achieve a more uniform cross section. Typically with flatter nuggets, you will also see a kind of folding in the copper. Okay, so once you've achieved a bar-like shape, you want to refine the points. And this will be done using a smaller rock tool, just easier to hold. Okay, when shaping the points, you want to hold it at an angle and hit away from the center to kind of draw that point out. Has a nice square shape. I can still feel the heat a little bit from hammering, and you can also see little flakes coming up off the copper. At this point, when you have a shape that you feel is adequate, you want to anneal it after this.
Previous experiments replicating copper artifacts have told us a great deal about this technology. Some of the more recent experiments have focused on annealing, the process of heating copper in order to allow it to recrystallize, thus becoming malleable so that you can begin working it again. If you work native copper for a while with a stone, it becomes very, very hard and brittle, but if you frequently stop and heat it up, anneal, then you can continue working this material. So a lot of experiments have focused on that specifically, and we also looked into that in this experiment.
We believe that after they cold worked the pieces, the prehistoric people would have heated them up in the fire or annealed them to relieve any internal stresses that may have arisen from the cold working. They would have needed a good temperature in the fire for this annealing, because you don't want it to be too hot so that the piece melts or becomes weaker, but you want it hot enough that there is something that relieves the stresses. An easy way to tell a good annealing temperature is by the color of the piece, actually looking at the piece as it's in the fire. We want a dull red, which indicates what we've measured to be around 700 degrees. That's the color that has been found to indicate a good anneal and a good annealing temperature. If it becomes cherry red, that's too hot, but if there's no red color at all, then that's not hot enough. The prehistoric people wouldn't have had temperature reading devices like we do here, so they would have used the color indicator method.
It would appear that pretty much everywhere native copper was used in the ancient world, annealing was part of this technology. However, our study and other studies have shown that it potentially is possible to make a useful tool by hammering native copper without annealing. In other words, if you can achieve the desired tool form before the tool gets brittle enough to actually fracture and break, then annealing isn't necessary. But annealing buys you a lot more working time to achieve the final desired form.
So now we'll remove the piece very carefully from the spatula that we used. It's cooled down a little bit, but it's still pretty hot. I think it measured around 600 degrees. It did achieve the dull red color that we wanted, so we know that it's been annealed. We're going to leave this one to slow cool on this rock here. That allows the grains to nucleate and grow as it cools to achieve a more uniform microstructure.
A key step in identifying processes performed on metallic pieces is looking at its microstructure. To get a better look at the microstructure of the cold-worked and annealed awls, Mara and Jenna will use metallography, or the study of the structures of metals, especially with a microscope. The microstructure of a metal artifact is made up of the structural features, such as grains, that can be seen under a microscope. They will be using the optical microscope in the Materials Engineering Optical Microscopy Lab in Neil Armstrong Hall. The optical microscope shines light through a series of polarizing lenses with different magnitudes in order to produce images at varying magnifications. Before the microstructure of a sample can be viewed, it must be mounted, polished, and etched. The cut sample is first mounted in a mix of epoxy resin and epoxy hardener in a round mold. The drying process takes about 2 hours. Once mounted, the sample is then polished on a series of discs, similar to sandpaper, with decreasing grit size. The time it takes increases as the particle size decreases. As soon as most of the scratches are polished smooth, the sample must be etched to reveal the microstructure. An acidic solution of ammonium hydroxide and hydrogen peroxide is rubbed over the sample's surface to dissolve the top copper layer and reveal the microstructure underneath, which can then be observed under the microscope. The cold work piece has a microstructure with long grains that have been flattened due to hammering. These grains are more visible near the worked edges. The grains in the center of the piece have received less impact, so they are still stretched out, but not flattened. The grains in the annealed sample are smaller than those in the cold-worked sample, and are much more defined. This is due to the recovery, recrystallization, and grain growth that occurs during the annealing process. Cold working metal causes internal stresses in the metallic structure due to the dislocation of metallic crystals. Annealing or heating the metal relieves these stresses and causes the crystals to realign, forming new, smaller grains. There are some characteristics of an annealed microstructure other than the defined and uniformed grains. One of these features is annealing twins, or side-by-side linear grains. These are caused by crystals mirroring each other's structure, and are common in metals that are heated to 500 degrees Celsius or higher.
What we have here are the results of the experimental work that Mara and Jenna have been doing, making artifacts using native copper. They started with nuggets. So native copper is copper that occurs naturally in a very pure form, 99.9% copper, and can be found in a variety of sizes. So they started with some shape like this, copper that I had found previously on trips to Alaska. And what they set out to do was make a specific artifact, an awl. And so there are a few examples that you can see here, and these are what I would consider to be fairly typical for a copper awl.
Mara and Jenna set out to collect very basic information, such as the time and skill required to make an awl from copper, and why this material was chosen over bone or stone.
We made a couple of sheets, as you can see here, for annealing purposes. They're easier to find in the fire than the awls were. Number 9, we cut off a sample here. As you can see, it's cut. We mounted and polished that sample for microstructural analysis. Number 14 and 15, you can see little dots on the interior surface of the samples. Those were from the hardness testing that we performed on the pieces. The difference between these two, they were both annealed, but one was quenched, 14 was quenched, and number 15 was slowly cooled. So we did hardness to tell the difference between those two.
One of the other things that came out of this study is in the process of working native copper, sometimes the nugget they were hammering on broke, and there wasn't enough material in the broken pieces to continue working one of those. This provides us additional insight into archaeological context and helps us interpret the many pieces of native copper from sites such as the Gulkana site that don't appear to be finished tools, and they're just sort of bits and pieces of copper.
Number 13 and 5 here are examples of failed attempts, and basically because the nugget broke as we were shaping it.
So what we may be looking at in some of these instances are material failures where the copper nugget was being worked by somebody, but it broke and wasn't able to be repaired or fixed or continued to be used.
As we were shaping it. And with number 13, we don't have enough material to work with, so we just left it as is. Number 10 here is actually an example of a larger nugget that we were shaping into an awl, which broke into 3 pieces, and this piece was actually large enough to continue shaping.
And especially if one has a large supply of copper nuggets, there wouldn't be a great deal of motivation to make use of every little scrap piece of copper necessarily. If the nugget you're working on broke, you might just leave those pieces where you were working and start fresh with a new nugget of copper. We're attempting to demystify this technology a little bit. It allows us to know a little bit more about the past use of copper and to be able to interpret copper from archaeological context. So for instance, the Gulkana site, where we have a lot of artifacts like these awls, this experiment gives us some idea of how much time it took to actually make this material. So the artifacts that we find in a particular feature at the Gulkana site, is this something that could have been done in just a day or half of a day? This experiment is part of a larger program of research into the use of native copper in far northwest North America. And this experiment is also a crucial part of a behavioral archaeology approach. So this study has provided insight into site formation processes. It helps us better understand the activities of the past that created the archaeological record at a particular site. And additionally, related to, or as part of the behavioral archaeology research program, this experiment gives us insight into the choices that people made with respect to technology, why certain materials were used for different tools and different tasks in the past. It helps us better understand the trade-offs involved in using one material or technology versus another in any given situation. And so again, this provides us information that helps us develop hypotheses about innovation, why innovation of a particular technology occurred. So why would the use of native copper in the past have spread throughout a region or not? What were the limitations on using this technology, and what were the benefits in comparison to other technology that was available?
But you know, the idea was that potentially it would be a huge, like, people sort of go overboard with the value of copper. Like, well, I mean, nobody would would leave it behind, but that's ridiculous. Like, it was just another raw material for tools, and so, you know, you lost one. So what? You got a big pile of nuggets, you can just make a new one to replace it.
Right. Yeah. I was interested in the class, then you told me about this opportunity, and so it was perfect because I wanted to apply my materials engineering to archaeology.
Not everyone in anthropology that's majoring in anthropology gets opportunities to do projects like these. So I really feel that I've gained a lot of experience with hands-on and experimental archaeology through this process.